Hello everybody, this is Mr. Ray with our next lesson in the MCV course. We are actually today, we are officially finished with the vectors portion of the course, and we're about to begin calculus, which for those of you headed to university and will be taking calculus, this is, you'll be learning this in first year calculus. So we are trimming down the content based on the reduced number of learning days and our distance learning, but we've got together as teachers of calculus and decided what's most important. So you should see an overlap with the other students for the other calculus teachers. The same things should be taught. So you should be able to help each other out between classes as well. Okay, first thing is I'm going to do a very quick high-level overview of calculus, and for those of you that saw the University of Waterloo link that I gave you for the review, if you take a look at the introduction to calculus, they do a really good job of what I'm about to explain. My version is probably half the length of time. So basically there's two components to calculus, okay? The first part is what we'll be doing in this course. So basically in calculus, you start with some kind of function. It could be a polynomial function, it could be sinusoidal, it could be exponential, it could be anything. So I'm just going to draw some sort of polynomial, graph of a polynomial that goes on. The first part is of calculus is to determine the slope at any part of that function. So basically, we did a little bit of this in in advanced functions. For example, if I wanted to know the slope at that point right there, you would take a tangent line, you would draw the tangent so that it only touches the graph at one point. Now you can tell from mine's not very good. You can see it's, it's not perfect. But if we took that point and another point on that tangent and figured out, well, what's the slope of that line, that would be considered the slope at that point. Okay, now you can see doing it graphically is not very good, not very accurate. So in calculus, we have an algebraic method of doing it that's exact. Okay, so the first part is basically finding the slope at any point on a function. Okay, and we do that, like I said, this is a tangent line. Now, for example, if this was a graph of somebody traveling somewhere, the distance from home or something like that, you could use this slope to calculate the person's speed at that instantaneous point in time. And you can kind of see from here where they kind of turn around and come back. That's sort of like a local maximum. That would be the slope at that point would be 0 because their speed, they basically stopped for an instant, and then their speed would be now increasing and coming back. So we'll learn all about that later on. Now we actually take it a little bit farther too. Like once we find the slope at that, if we did it again, well, before I say that, we call what we're doing here, find the slope at any point of function. We call that differentiation. Differentiation. We don't often use that term. A lot of times we'll just say taking the derivative. So that's the key word here, derivative or differentiation. If we take the derivative of that point, we basically get the speed. Now, if continue this process, if we took the derivative of the derivative, we call that the second derivative. And if I wanted to find what's that person's acceleration at that point, we could do that through derivatives as well. Okay, so that's what we're going to be doing in this course. We're just going to be looking at this part of calculus. The other part of calculus, I could take, well, it's not going to be exact, but I could take another function, and if I wanted to, for some reason, I want to find the area between 2 points on that function. If I wanted to calculate the area under the curve, okay, that's the second area of calculus, finding the area under a curve or under a function. And obviously that's, you have to designate which 2 points you're doing this for, the beginning and the end. So that can be a very useful form of mathematics, and what we call this is integration, or if we put it in a sentence, taking the integral. Okay, now unfortunately, when they redid the calculus course about 10 years ago or 13 years ago, they basically merged it with vectors. So when they did that, they basically took this whole area right out of the course, which I think is really unfortunate, because it's probably the most interesting part of calculus, and in first year calculus in university you will be doing this. So I just want to put in perspective, there's two forms of calculus. We'll just be looking at differentiation and not integration. Okay, this, just like this differentiation, you can extend it, taking the second derivative to get the acceleration. You could get some really interesting things here. If you had a three-dimensional shape, you can actually find the area, the volume underneath some kind of function for the shape by doing a double integral. Okay, so it kind of relates back to doing this twice, just like we did with the derivative. Okay, so that's all there is for what is calculus. Now, what we're going to do today is I'm just going to first start off with part of lesson 1, which is basically just kind of an introduction. It's a skill we're going to need in a couple of lessons from now. It's also a skill that you've done in grade 11, and I think we used it again in advanced functions. So what I'm going to be doing, I'm just taking the second page of the first lesson, and if you remember this phrase, rationalize the denominator, okay? What that means usually is we have some kind of rational expression that has a radical or a root on the bottom, and mathematicians really don't like that. So what we try to do is rationalize the denominator. In other words, make it so that we make the equivalent rational expression that doesn't have a radical on the bottom. So for example, when we say simplify this by rationalizing the denominator, we can multiply. This is fairly straightforward one. We're going to multiply by basically 1, which is what do we need to multiply this by to get rid of the root? And that's just to multiply by the same root again. So if I multiply the bottom by root 5, I'll multiply the top by root 5, and basically this whole thing is equal to 1. So we're not changing the value, we're just changing the way it looks. So on the top, if I multiply 3 with root 5, I just get 3 root 5. And down here, I'm multiplying 4, basically 4 times root 5 times root 5. Now, you could do this a long way and just say, well, root 5 times root 5, that's root 25. Oh, that's 5. But what I'd like you to think about, a more direct solution to this is like root 5 all squared. So it's basically, you're basically canceling out the square root function by squaring it. So root 5 times root 5 is just 5. So that basically turns into 4 times 5, which is 20. Now at this point, you try to see if you can reduce this. So obviously the root 5 will have no play in this, but basically you're saying, can I reduce 3 over 20? And in this case, you can't. So that is your simplified version with the denominator rationalized, okay? Now, what happens when you have a denominator that has 2 terms, in other words, a binomial. So what we need to do this time, okay, so we start off with the original. Now again, we're going to multiply by something that's going to get rid of this. If you remember from grade 11, what we do is, if I just put brackets around there for the sake of it, we multiply by the conjugate. Anytime we have a binomial with a radical in it, we use the conjugate. So the conjugate of a binomial is very simple. It's just the same terms with the opposite sign between them. So in this case, the conjugate of root 6 plus root 3 is root 6 minus root 3. Okay, and so we're going to multiply that bottom and top, which is, again, that's just equal to 1, so we're not changing its value. Now, on the bottom here, I'd like you to do a shortcut. You probably, hopefully remember this. This is difference of squares. It's like a plus b times a minus b. So the shortcut for that will just be this term squared minus this term squared. Okay, because if you did your FOIL here, you're going to get a minus 3 root times root 6, sorry, a minus root 3 root 6, and here you're going to get a plus root 3 root 6. They're going to cancel. So it's really just works out to this squared. So root 6 squared is 6, and root 3 squared is 3, but remember it's minus, it's going to be this squared minus this squared, so it's just 6 minus 3. And you can see, you know, how that relates to the original binomial. On the top here, we can't really do too much. We could expand it, but basically it's 2 root 6 minus root 3. We can't cancel these. These are not multiples of each other. Now I could simplify the bottom. It's just 3. And if I want to simplify, that means expand it too. So that's 2 root 6. Now, if you're thinking about this, the 2 that's up here and the 3 that's on the bottom, I can't do anything with that in terms of simplifying. And you have to look for that. So if I expand it, it's 2 root 6 minus 2 root 3 over 3. So that's the denominator rationalized. Again, this time we're going to use conjugate to rationalize this denominator. So hopefully you'll know what we're going to multiply here. So originally, I just put brackets around to, for me it makes it clearer. So on the bottom here, the conjugate of that is just 2 root 6 minus 3. Okay, and even though we don't have to rationalize that 3, we still have to use the conjugate to get rid of that root 6. So anytime you see any kind of binomial on the bottom with a radical in both or one of the terms, then you just take the conjugate and multiply both numerator and denominator by that. Okay, and you can see the conjugate just changes the signs. And again, this is just 1. If I multiply the bottom here, again, it's, if you take the shortcut, it's this squared. Sorry, it's the 2 root 6 squared minus 3 squared. So think of 2 root 6 as 2 times root 6 times 2 times root 6. That's what it is. So you have a 2 times 2, which is a 4, times a root 6 times root 6, which is 6. So it's 4 times 6. So you have a 24 on the bottom. That's from your first term squared. And then the second part of that is subtract the second term squared. So minus 3 squared, which is 9. Okay, and on the top, this time I'm just going to leave it, well, I'll leave it not expanded, 2 root 6 minus 3. Now this works out to be 15, and I'm still going to leave it unexpanded. But now you can see the reason why I did that was I want to be able to reduce before I expand this. And I can see here 5 and 15, I could reduce that to 1 over 5, sorry, 1 over 3. So when I reduce that, I get 2 root 6 minus 3 over 3. Okay, so that's That one's a little bit tougher. Okay, sec here. Okay, now this last one, if you look at the instructions, it's kind of different. It says rationalize the numerator. Now, why would we need to do that? Because math people don't really care. This would be fine. But the reason why we're doing this is for this is what we're going to be doing in calculus. We're going to, at some point, we're going to say, okay, we're going to rationalize the numerator. So it's exactly the same, except instead of getting rid of the radicals on the bottom, we're getting the radicals in the numerator. So you'll see why we want to do this later on, but for the time, let's just practice one, okay? So this is root 7 minus root 3 over 2. Now, again, I'm going to multiply this by the conjugate of root 7 minus root 3. That's root 7 plus root 3. Same thing on the bottom. Okay, now let's start with the top because we're doing our rationalizing up here. So this, again, this is like difference of squares. So it's root 7 squared, which is just 7, minus root 3 squared, which is 3. And on the bottom, 2 times root 7 plus root 3. I'm hoping nobody's asking, well, why doesn't he add these two together? You can't. You can't add radicals together. You can multiply them together. For example, like we did here, root 7 times root 7, that's root 49, which is 7. Okay, now if I simplify it on the top, and again, just like before, you'll see, oh, we can actually reduce this. 4 divided by 2 is 2, 2 divided by 2 is 1. So I get, oh, sorry, that should be a 7. So I get a 2 over root 7 plus root 3. Okay, so that's just a quick little bit of a reminder on how to do this. We did it in grade 11 for sure, and also I believe you would have encountered this in advanced functions. Okay, so that's the part of lesson 1. I don't think you really need to practice that unless you're having difficulty with what I was explaining there. Okay, so what we're going to do now is the bulk of this lesson will be lesson 2, which will be our lesson 1 for this course, for the distant learning part. And we're doing the slope of a tangent. So if you remember from my, where is it? My initial description, here it is. My initial description of calculus, we're doing the slope of a tangent. That's exactly what I was talking about here. We're finding the tangent line at any point along a function or curve, finding the slope of that. So that's what this lesson is introducing. So it's a bit, it can seem, for some of you, it might seem a little complicated. But please go back and listen again or check the textbook. They have some good parts on this. If you want to know where this is in the text, just follow from where the homework assigned is and, you know, turn a few pages back. Okay, so slope of a tangent, definitions should be familiar. Secant, well, let's start with tangent. Tangent's a line that crosses the curve at one point. Also, if you drew a line, it's a straight line that most resembles the graph near a point. Now, a secant, hopefully you remember this. This is a line that crosses a curve at 2 points. Okay, so we'll be talking about both of these when we do this lesson. So make sure you understand secant crosses twice, tangent crosses once. Okay, now the conjugate, that we just did that. So that should be relatively recent for you to remember. Okay, now I'm going to zoom in on these pictures down here. So I want to make sure. Okay, so the first graph, you can see the blue curve. That's our function f of x, and these t lines, t1, t2, t3, t4. These are tangent lines at points on this function f of x. So they didn't actually put where the points are here, but I could, give you a pretty good idea. T3, it's probably about halfway. So basically, T1 is the tangent at that point on f of x. T2 is the tangent line at that point on f of x. Same thing here, and you notice tangent 4, that looks like a line that's basically no slope. And I think we talked about this earlier. This is where you have a local minimum. So at that point, the slope is 0, and that's going to be very useful in calculus later on. Okay. Now, once we have these tangents, it's pretty easy to get the slope. You just take any 2 points on the tangent and do your delta y or change of y, change of x, or your rise over run gives you the slope. Okay. Now, here's how we're going to do it in calculus, at least at the beginning. So this is a very important graph, and then we're going to change this into kind of a rule. Okay. So here's again, the blue curve is your f of x. Okay, it looks like part of a parabola almost. We want to take the tangent at this point P. Okay, so if we were to draw the tangent, it would be our red line here. Okay, but like I said, it's pretty hard to do an exact perfect tangent line. If it's off by a little bit, it won't be right. Okay, so what we do, remember a secant is a line that crosses the curve at 2 points. So we have a whole series of secants here. We haven't labeled them, but these dashed green lines, it's basically secant lines that go through P and also go through another point Q. Okay. Now, if I was to take the slope of that secant to try to approximate this tangent, it's not all that close, right? But you can see as Q becomes closer and closer to where P is on this curve, for example, if I change Q to over here, there's my new secant, and that's getting closer to what this tangent is. And if I change it to that Q, it's getting closer. And you can imagine as I move Q closer and closer down this to P, as that distance approaches 0, that secant turns into a tangent. So that's the strategy we're going to use when we try to come up with the slope of a tangent. Okay, we're going to be using basically, instead of what's the slope of the tangent, which it's hard to do, we're going to approximate it based on the secant, where that distance between P and Q gets smaller and smaller to the point where it's 0. Okay. All right. So let's read this rule here, and then we'll see how it works. Okay. So the slope of a tangent to a curve at point P. So let me get back in. So again, if we're trying to get the slope of the tangent at that point, is the limiting slope. So limiting slope means, well, we'll get to that in a second, but slope of the secant PQ as the point Q slides along the curve towards P. In other words, the slope of the tangent is said to be the limit of the slope of the secant as Q approaches P. Okay, so that word limit, we're going to see that a lot. So we'll learn what the limit actually means. So hopefully that makes sense. We're going to try to figure out what's the slope of the tangent by getting, well, what's the slope of the secant as this point Q, which is the other point that crosses, that's on the function, as it gets, basically what they said, as it slides towards Q. You could see that the closer Q is to P, the closer that slope of that secant will be to the slope of the tangent. Okay. I know it's a little bit out there at this point, but let's try this out. Okay. I'm going to zoom back out. Okay, now up here we have it. Let me zoom back in a bit. So we're going to, based on what we just said on the previous page about the slope of a tangent, that was all just words. So let's try to make it more mathematical. Okay, let's zoom in. Okay, so the slope of a tangent as a limit. Okay, slope of the tangent to the graph y equals f of x at a point P. So basically we're saying that point P has x coordinate A, and the y coordinate will be if I plugged A into the function. Okay, we don't know what that function is here, it's just generic function f. So that's the point P that we're trying to find the tangent at. So what we're going to do, remember m is the variable we use for slope. Now here's some new terminology here. The slope is equal to the limit. Now you should remember delta y over delta x, that's really rise over run, as delta x approaches 0. Okay, now delta x, that's basically as the run approaches 0, or in other words, as the 2 points that we're calculating the slope for become closer and closer together to the point where they become the same point. Okay, so don't be too overwhelmed with this at this point. We'll be talking about that quite a bit. So if I expand delta y over delta x, that's rise over run. So in this, I've still got limit. Now what I'm doing here, remember the point P has x coordinate A, and the y coordinate will be f of A. So if I define a variable here called h is basically the difference in x, the difference in the x coordinate, in the value of x between the 2 points P and Q. So A plus h, this is, 1 second. So this point here, this is your A plus h, that's your P point. Sorry, that's your Q point, because f of A, that's your P point. So what you're doing here, these are the y, so because it's f of A plus h and f of A, these are your y coordinates of Q and of P. So basically this is on top, this is the rise, okay, the difference in the y value, okay? And then on the bottom is your h. So this can be a little confusing at first, but the x coordinate of Q will be x plus h, all right? And the x coordinate of, sorry, it's A plus h. So that's the x coordinate of Q. The x coordinate of P is just A. So if I found the difference or the run, it's A plus h minus A, which is just equal to h. So that's why the h is on the bottom. It basically, that's the difference between the 2 points. But you're trying to simulate as h becomes 0, what is this slope? Okay. Now, it also says if this limit exists. Sometimes it doesn't. Sometimes we have to work on it, and that's what we'll be doing. So you'll notice limit as h approaches 0. Using this formula, if I just said, well, okay, let's just make h 0. If I plug 0 in here at this point, I get some number over 0, which is undefined. So you're going to see we have to actually do a little bit of work. We can't. It's not just plug it in and get the number. It's going to be some work. Okay, so there's our. Let me zoom back out. Okay, so hopefully this example helps show you what we're doing here. Okay, so find the slope of the tangent and using the function y equals x squared at the point 1, 1. So basically, you know, if you did a graph y equals x squared and say this was 1, you're trying to find, what we're trying to do is find that slope. This is our well, this is our m value. Okay, so we're gonna do it by, okay, so the point we want to do this is 1, 1, so I'll call that P, and what we're gonna do is I'll have another point Q that will be to the right of P, and what I'm gonna do is as we get points, as Q gets closer and closer to P. So I've actually got, I'm gonna come up with some values of, of Q and do our calculation of the slope from there. So we've already got our point P, which is at 1, 1. We know it's because that's what was given. 1 squared is 1, that's why it's 1, 1. Now point Q, let's start off with, say the original Q is at x equals 4, which is, it's going to be pretty high. I can't even draw it on here. So if x is 4, then y will be 4 squared, which is 16. Okay, so what I'm going to calculate here is delta y over delta x. And I'm going to be doing that for these different values of q. And you'll see, we can see a pattern that we're going to use. So if I do delta y over delta x, I'm basically saying change in y between p and q. So the y is 16 minus 1, 16 minus 1 over 4 minus 1. So in this case, that's 15 over 3. So the slope is equal to 15 over 3 is 5. So if basically the slope of the secant between P and Q, where, in that case, the slope of the secant is 5. It's probably going to be pretty far off from what we really want, but let's get closer and closer. So if I move Q a little bit closer to P, remember P is at 1, right now Q is at x equals 4. Let's try x equals 3. So if x is 3, then y is 9. I do our delta y over delta x. So again, we're not using this point, we're using Q2 and P, so 9 minus 1 over 3 minus 1, so that's 8 over 2, so in this case the slope is 4. So you can see by moving Q a little bit closer to P, our slope is decreasing. It went from 5 to 4, and that makes sense because as I get closer, the tangent will get smaller. The slope will get lower. Okay, a decrease. Let's try Q being 2. The x value for Q3 is 2. 2 squared is 4, so that's the point Q3. If I do my delta y over delta x here, it's 4 minus 1. Sorry, I should write this at 4 minus 1 over 2 minus 1. So this time it's 3. 3 over 1 is 3. Okay, so you can see gradually my slope is decreasing. So where will it actually go to as this distance between P and Q gets so small? Okay, so we're now at x equals 2. So let's try 1.5. Because remember, P is at 1, and now Q is at 1.5, so it's getting pretty close, the 2 points together. 1.5 squared is 2.25, and if I do my slope here, it's 2.25 minus 1 over 1.5 minus 1, and if you do that calculation, you get a slope of 2.5. Okay, so it went down by 1, went down by 1, now it went down by 0.5. How far will it actually go? Will it go to 0? Will it go to negative? Probably not. So now let's go even closer. If for Q5, if x was 1.1 and we square that, we get 1.21 for y. If we do our delta y over delta x, that's 1.21 minus 1 over 1.1 minus 1. And if you do that calculation, you have to round this time, 2.1 approximately. Okay, so it seems to be slowing down. Let's try one more point, say Q6, and this time we'll get really, really close. How about 1.01? If I square that, I get 1.0201. Sorry, that should not be a point. Okay, and if we do our, well, I'm not even going to do that, but if I did the slope calculation between Q6 and P, this time I would get approximately 2.01. Okay, so you can kind of see the trend here, decreasing as Q is getting closer to P, the slope is getting closer and closer, and you can kind of see here, it looks like it's not going to go below 2. It looks like it's approaching 2. Okay, so what we'll say here is therefore the slope of the tangent to y equals x squared at the point 1, 1 is 2. Okay, and that's kind of, I mean, that's not totally scientific, but we're just looking at the pattern here. If you went lower and lower, 1.001 and so on, you'd see that this number, this part will be getting closer and closer to 0, which means the slope's getting closer and closer to 2. Okay, and we just make our, prediction based on some evidence that it looks like the slope is 2. Okay, but we'll do better than that. This time we're going to do more, like a little bit more algebraic here. So we're going to do the point P and Q. You can see Q here. It's kind of what we were doing here. We're just coming up with values of H up here, but this time we're just going to generically use H. So let's see what that is. So if we're doing the slope between these points, it's basically going to be this y coordinate, which is 1 plus h squared, minus this y coordinate, which is just 1. So this is like y2 minus y1. And then the bottom we have x2 minus x1. So this is 1 plus h minus 1. And you can kind of see that's what I was talking about at the top here. The bottom just becomes the h value, the difference between the 2 points. So when I simplify this, you can see on the top, don't forget this is not 1 plus h squared. This is 1 plus 2h plus h squared when you do your expanding, and then we subtract 1. Now in the bottom here, well, the 1 minus 1, they just cancel each other out, so I just get h. And also on the top here, you can see I also have a 1 minus 1. They cancel each other out. And I'm going to have 2h plus h squared over h. Well, I now divide out by h, and I get 2 plus h. Okay, so I've got a formula for the slope based on the value of h. Now what we really want to do is make h so small that we consider it to be 0, that p and q are the same point. So this is where the exactness comes in. We say as that difference between the 2 points approaches 0, our m approaches or becomes 2. Okay, which matches up with what we said here. The slope at the point 1, 1 of y equals x squared is 2. Okay, so this is kind of the approach we're going to be using when we do slope of tangents at the beginning of this course. Okay, so we're going to do one final example here for this lesson. We're going to take a slightly more complicated function, still a quadratic, but not just x squared. It's 2x squared minus x plus 4. We're going to do this two ways. Okay, so basically I'm going to draw a line down the middle of the page because it says find the equation of the tangent line of this at x equals 1, then develop an equation of the same tangent line for any point on the curve. So we'll talk about how that works. So on the left here, I'm just going to do what the first part of the question was. We want to find the slope. So we'll just kind of put our goal here, find the slope at x equals 1 at the point 1, 5. Now I'm able to say it's 5 because if you plug in x equals 1, you'll get 2 minus 1 plus 4. So it's basically we're finding the slope at that point on f of x. Okay, so here's where we start doing our new terminology. Okay, so when you're doing questions, it has to be written like this. So now M stands for slope. I'm going to put a little subscript here, and I'm going to put the word or the abbreviation tan. That refers to the slope of the tangent. Okay, so M tan. Okay, and that's going to be equal to the limit as h approaches 0. Remember, h is going to be the difference between the 2 points. One point being 1 and the other point being 1 plus h. So again, we're going to do the limit of the rise over run, delta y over delta x. So that's going to be f of 1 plus h. That's going to be our q. Q is h units to the right of point P. And then we subtract f1, which is our point P, the y, basically the y value at point P. And then on the bottom, it's going to be the change in the x value, which is 1 plus h. That's our x coordinate for Q. You can see it up here, and then subtract the x coordinate for point P, which is 1. Okay. Now, a habit that I catch myself doing once in a while is to kind of drop this as we're doing our solution here. You always have to keep this limit in here. So don't forget to keep it in there. Okay, so now what we can do, this is where it becomes a little bit complicated. So what we're going to do is, here's our function f of x. We're going to plug 1 plus h wherever we see an x. So f of 1 plus h is equal to 2 1 plus h squared, because you plug in 1 plus h for x squared, minus 1 plus h plus 4. And then we subtract f of 1. Now f of 1, that's the x coordinate at that point. That's just subtract 5. Okay, and then the bottom, you can see, well, 1 plus h minus 1. Well, the 1's cancel. We're just left with h. Okay, so now we can we have a bit of simplifying on the numerator. So I'm not going to skip any steps here. If I squared that, don't forget it's not 1 plus h squared. It's actually 1 plus 2h plus h squared. And then I have minus 1 minus h. And I can put these two together at this point. Plus 4 minus 5 is minus 1. Still all over h. Now, what I'm going to do is expand the brackets here. So I get 2 plus 4h plus 2h squared. I can put these two minus 2's together. So 2 minus 1's. And I get that over h. And you can see I've got a 2 and a minus 2 here, so they're going to cancel. So you can see we're getting something more simplified at this stage. So what I have left here is I have a 4h minus h, so that's 3h, and I have a plus 2h squared all over h. Okay, now remember I was talking about this limit as h approaches 0. Well, if you can plug in h equals 0 here and have something that makes sense, well, you should do it. But in this case, if I plug in h equals 0 anywhere along here so far, it gets we put a 0 on the bottom, and that divide by 0 is not allowed, so I can't actually apply this yet. Now as soon as I simplify this, I can divide both of these terms by h, so I get 3 plus 2h. So you notice I got rid of the h on the bottom because each of the terms in the numerator had an h. So at this point now I can say, hey, look, I can plug a 0 in for h. So I get the slope of the tangent is equal to, as I plug 0 in there, it's equal to 3. Okay, so that's the slope of the tangent at x equals 1 for f of the function f. Okay, now it also asked, use the equation to find the slope of the, okay, so that's the next. Now, it says find the equation of the tangent line. Okay, so far we've just found the slope of the tangent line. So if you remember back to your grade 9, if that's your m value, you have y equals 3x plus b. And then we do have a point that's on this. The only point we actually know that's on this tangent is our point P. So that's, I can plug in x equals 1, y equals 5. And I get b equals 2. And therefore, the equation of the tangent, is y equals 3x plus 2. So I plugged in 1, 5 here. Okay, so that's the slope of the tangent at point P, and the equation of the tangent, we just used the slope, plugged in the point that's on the tangent, and that's our equation. Okay, so the second part of this, now the problem here, if you can imagine, say part B of this question was, okay, now find the slope at where x is equal to 4. We'd have to do this whole thing all over again, and that can be very time consuming. So what they want us to do is develop an equation of the same tangent line for any point on the curve, okay, and then use this equation to find the slope at any 3 other points on the curve. Okay, so we call this the general slope formula. And you're going to see this is a little more useful than finding it for a specific point. So we don't actually know the x value, we're just going to call it x and y. Okay, so if we go back and do our m tan, it's going to be the limit. So I'm going to kind of do the same thing I did over here. Limit as h approaches 0. Okay, so if P, we're still going to use points P and Q, but point Q is going to be x plus h, and then f of x plus h. Okay, so our change in the y is basically what's the value of f of x plus h. So all right, so that's going to be f of x plus h minus f of x, and then x plus h minus x. This is the point Q. It's got x squared and x plus h. Sorry, it's got y coordinate x plus h, y coordinate of f of x plus h and y coordinate x plus h, and the original point P, again, that's we're just going to call it the point x comma f of x generically. Okay, so it looks a little harder, but it's not. So what we're going to do is plug in x plus h. So before we plugged in 1 plus h, wherever x was in the equation. This time we're just going to plug in x plus h. So we get 2x plus h squared minus x plus h plus 4. And then now we plug in f of x. Now f of x is just the original equation. We don't know its value because we don't know what x is. So it's basically subtract f of x, so subtract 2x squared minus x plus 4. So it looks a little long on the top at the beginning, but it will simplify very quickly. On the bottom you can see I've got x minus x. They cancel each other out, and as usual I get h on the bottom. Okay, now if I expand this out, I'm going to kind of do the whole thing here. Square x plus h and then double the terms. I'm going to get 2x squared plus 4xh and plus 2h squared. Okay, so that part, it just comes from 2x plus h squared. And now I have my minus x minus h plus 4. Now this, I have to apply the subtraction to inside the brackets. So minus 2x squared plus x minus 4. Okay, so that's a lot on one line, but a lot of this cancels out. Okay, you can see I've got 2x squared minus 2x squared. They cancel out. I've got minus x plus x. They cancel out. And I get a plus 4 minus 4. So everything over here just canceled with something that was already there, and still all over h. So what do I have left? I have 4xh plus 2h squared minus h all over h, and you can see every term on the top has an h, so I can divide the h out from the bottom, and I get, so that cancels, I get one of these canceling, I get this becomes a minus 1, so I get 4x plus 2h minus 1. Now again, since I was able to cancel out the h in the denominator, now I can actually substitute in a 0 for h, so I can do the limit here and say, oh, that's just equal to 4x minus 1. And that's the slope of the tangent. So very important there. So what does that mean? Why did we put ourselves through all this trouble? Well, now I can actually find the point, the slope at any point on this curve just by plugging in the value of x. Now one thing we can do, I could say, well, let's just check to see if this works. So the first point I'll do, well, what if we want the slope at x equals 1, which is basically what this question was. So if I plug in x equals 1, I'll get 4 times 1, 4 minus 1. The slope is 3, and that matches up with what we got over here. Okay, so let's try for other points. Let's do at x equals negative 4. I plug negative 4 in here, I get negative 16 minus 1. I get the slope of that tangent is negative 17. That means it's the tangent is going down to the right, which makes sense because it's on the left side of probably the vertex. Let's try another point. How about x equals 0? So I plug x equals 0, I get 0 minus 1, which is minus 1. And one other, this isn't a random point, but you'll see why I picked it. How about 0.25? If I plug 0.25, I get 1 minus 1. 1 minus 1 is 0, so the slope is 0. Okay, now slope of 0, that we're going to find out later on, that actually is, that's going to be a local min or local max, because that's where the curve is changing direction. Okay, so this has been a very long lesson, but what I would like you to do is try some of the homework questions here. I'm going to try to give you 2 other lessons this week with an assignment at the end of the week that you would submit like you did this week. Okay, so hopefully that makes sense to you, and if not, use the textbook or go back and listen to parts of this you didn't get. Okay, thank you. See you tomorrow.